Perfect, thanks. Hi everyone, I'm really happy to be here. Yeah, so technically right now I'm not yet a professor. I'll start my appointment in about a few weeks, but so currently I'm a postdoc at UC Berkeley, and then I'll be starting at Cornell Tech, which is essentially Cornell, but they have a graduate campus in New York City now. And so I'll be based there starting in a few weeks. So I'm really happy to be here and to talk about some of my work. And so the work I'm going to talk about today is with two student co-authors, Phaedra and Hannah, on so the title is fairly long. It's Dropping Standardized Testing for Admissions, Differential Variance and Access. And before I dive into the regular spiel, I'll sort of just give like a little background in that this is part of a fairly active debate, at least in the United States. I'm sorry, I'm not very well familiar if there's like a similar debate in the Iranian context, but in the United States right now, there's quite a lot of sort of active debate about the use of standardized tests in admissions, and more generally, sort of the theoretical model under the paper, and the theoretical part really just extends to thinking about if you have any set of features that you can require when making admissions decisions, how do you decide which set of features to do? Should you sort of keep all of them, or should you drop some of those features? And sort of from just like a purely Bayesian rational decision-making perspective, you might think, hey, look, keeping all the features are the right thing to do. And like, why would you ever want to drop some information? But at least in the United States, right now we're seeing that a lot of universities are going through this phase where, I mean, partially due to the pandemic, so partially due to like people literally just not being able to take the test because of COVID, but also due to other reasons, universities are dropping things like taking the SAT for undergraduate admissions. Or for graduate admissions, like not taking things like the GRE, which historically have been the two most common standardized tests at the college level of the US. And so this happened at the University of Chicago. This happened at the university, like the entirety of the University of California, including Berkeley, no longer does like the SAT for undergraduate admissions. And a lot of schools are doing this. And so the active debate right now is like, what is going to be the purpose? Like, sort of, what is going to be the effect of dropping these scores, and why are these schools even doing it? Sort of on one side of the debate, you have people who think that this is going to lead to sort of just like less prepared students being admitted. That standardized test scores are an important aspect of ranking students, of sort of figuring out who are the most meritorious or the most academically qualified students that you want to admit. And the worry is that, sort of like exactly like what I was saying earlier, tests are simply another way that you can get information about students, and sort of dropping them is sort of just less information. And of course, sorry for some of the slides. I think some of the slides animations, I should have converted to PDF before uploading as a PowerPoint. But yeah, so the sort of they're of course just a systematic means of collecting information, and of course the given rationale by the universities was that, and I'll go into the literature in a little bit, is that tests are just sort of, for a variety of reasons, they are biased measurements of people, right? So people don't have access, or they're culturally specific, or for a variety of reasons, tests are not like these exact tests are not the right way to measure, to measure and rank students. But the response to that, of like why you might want to keep tests, is other components also display disparity. So for example, of course, between people in privileged universities and non-privileged universities, whether they had access to researchers to write recommendation letters for undergrad to graduate admissions. There's another particular one, yeah, and so there's another particular one that one is hinting at is um, sort of tests are not the only feature that people use in admissions, right? So, or more generally, you have an admissions problem and you have a set of features. And this claim, what I claimed here was in New York Times, and I'll explain it because again, there's some American cultural stuff perhaps in the text. But so the claim is that let's say you have a set of features, and for one group, for like a minority group, some of the features are just far less informative. So what this quote is saying is without test scores, someone from a little known school in the South Bronx, so the South Bronx is a neighborhood of New York City that is perhaps not quite not as privileged, that might be an understatement, but sort of not quite as privileged as some of the other parts of New York City. It's poorer, sort of the public high schools, well, it's New York, so all public high schools are, but like the local public high schools might be sort of lower quality, sort of less funding, and so on. And in particular, they just might be less familiar to like college admissions people, right? And of course, everything I'm saying is exasperated internationally. Sort of like American graduate schools are far more familiar with sort of American universities than they are with universities from other places. I do want to go a little bit sort of move on just because sort of I want to get to the math and the model and sort of the results a little bit. But yeah, so one factor of why you might want to keep tests is exactly this evaluation question. Is there the only way that you can evaluate certain students because there's just no other way to evaluate them otherwise? But on the other hand, people are pointing out that just like empirically, there's a lot of racial and socioeconomic gaps in test scores. Just because, for example, who might the test prep industry is like who gets a chance to just prepare for tests. So, for example, in the U.S., this paper found that 8% of lower income kids versus almost 80% of higher income kids use some of these services to prepare for tests at the undergraduate level. And then this other paper found that tests are just expensive. And so, in the U.S., it's sort of the tests are run by private private company that charges a lot of money to take these tests, and this is true at every level. And so this paper found that for every sort of like 10 lower income people who would take the test and would be ready if someone paid for the test and like provided them access, there's a bunch of other students, or for every 10 students who do take the test, there's another 5 students who just decide not to take the test for whatever reason, primarily financial or other access reasons. And as more anecdotal evidence, this year, again, partially due to the pandemic, and there's a bunch of other things going on, but most programs at UC Berkeley this year dropped the GRE requirements for master's admissions. And they saw a huge increase in the number of historically underrepresented minority groups. So people who racial groups in the US who historically did not apply to master's programs, they saw a huge increase in those programs. And so there's at least some evidence that tests are providing a barrier from people for people from even applying in the first place. And so this paper really tries to balance these two factors and sort of really tries to think about their effects. So the first one is tests provide useful information, especially if you use them correctly. And they provide useful information for students who otherwise there would be no other information about them. On the other hand, perhaps for the same students, these tests might be inaccessible. The test might be expensive, or they just don't know anyone who has ever taken who often takes tests like this, or not that many people in the area go to college, and tests are just another barrier. And so if you require the test, you're going to have more information on everyone, but some people just might not end up applying. And so in this paper, what we try to do is we try to have a model that tries to compare these two effects, or tries to weigh the competing effects of the information aspect and the the access aspect. And in particular, we look at how do keeping or dropping the test affect both the composition of students, of like social or racial, racial or socioeconomic diversity, and academic merit. So like, how do you end up admitting quote unquote the best students, and how does this heterogeneously, how does this differently affect individual students? And so most of the, so I would say like 60–70% of the paper is theoretical, and in the theory part, we quantify this trade-off between, I'm saying tests here, but really about any feature that you could use in an admissions problem, is they provide useful information, but they also exclude some people. And what we find is, at least in the US, I don't know about in the Iranian context, but in the US, the debate has very much been that, tests are a trade-off between diversity, so who gets admitted, and sort of academic merit, that sort of you want to admit the best students versus you want to admit the students with the socioeconomic mix. That's a character of the US debate. And what we find is that that's really not what the trade-off is. The trade-off is really about the information versus the access. And so dropping the test can help you on both diversity and actually academic merit. So you end up admitting quote unquote better students if you drop the test. On the other hand, dropping the test can be harmful for both of these objectives, or for many other reasonable objectives. So the trade-off is really not between objectives, but really about trying to think through these multiple effects of tests. And then, sort of in the remainder of the paper, we start looking at data, and we use data from the University of Texas at Austin, which actually where I went to undergrad. But yeah, so we use data from there on sort of not just like historical data found online on and sort of model, or sort of give an example of how universities can, in a data-driven aspect, make the decision on whether they should keep their test or not. Like I said before, like nothing in the theory, nothing, sort of very little from the rest of the paper is, besides the introduction, is dependent on tests as being the thing under study. More generally, this is just a multidimensional information framework that you can use to, we think, study sort of the effect of which data you have in fair machine learning. Okay, so that was a very long, I'm sorry, maybe I should have cut that a little bit, but that was a very long introduction. Now I really do want to go into the model and the theory, and hopefully have time for the data at the end. But before I do that, are there any questions? Okay, so then before I do that, I'll just do 30 seconds on, this work is really, I would say, part of two very different fields. So in the economics literature, there's quite a lot of work on the economics of discrimination. So you might have heard of things like so certainly from like the Becker and Arrow works on like, do we have statistical discrimination or do we have case-based discrimination? And then of course, this is part of a longer literature on in economics on school choice and admissions. And on the other side, there's fairness in machine learning and mechanism design, which is sort of more recently thinking about what is the role of data in admissions processes, or what is the role of data in just like machine learning problems in general. And of course, there's a lot of modeling work specifically on fairness in college admissions. Okay, so dive into the model now. So we're going to say that we have a set of students, that this is a continuum of students who have some true unobserved skill. And for simplicity in this paper, we're just going to say that they're distributed normally with some mean and some variance. And in addition, each student belongs to a socioeconomic group that I'm just going to call Group A and Group B. And group membership is uncorrelated with the true skill. So we just make that assumption right off the bat. And then for each student, you don't observe these true skills, but you observe a noisy feature set. So, okay, so some of the slides are having some trouble. There should be some math that popped up. I'll just sort of explain what the math was for each student, you just observe a set of features, theta, which is just drawn from a normal distribution that is centered around Q. You have a set of essentially IID observations per student, and each feature can have different variants, for example. And then using those features, the school is just going to do the Bayesian optimal estimation process. They're just going to say, given all the features I have, what is the posterior mean of the student's skill distribution? And then they're going to admit the mass of students with the highest skill estimates. So I'm just going to do a cutoff on sort of the skill estimates and then admit everyone who has a score above the cutoff. And then hopefully the math pops up at some point. I think it will in a little bit, or it may not, we'll see. So just want to point out a few assumptions. The true skill distribution that we have is identical for both groups. So we're going to assume that the same distribution is there for groups A and B. Okay, I'm going to try to skip forward a little bit and see if the math can pop up in a different slide. Okay, no, it doesn't. Okay. So I'm trying to think about the best way to do this. So share screen. Okay, so people can see my screen. Okay, cool. So and then can we? Okay, so yeah, so I'll just walk through the math. Now I don't want to start the presentation mode just because the sharing. Okay, so okay, yeah. So let me just explain. So this is all the math. Let me just explain everything from this slide. From this slide. So we have a set of features, theta 1 through theta k for each student, and like I said, they're distributed with a mean that's centered around the true skill plus some bias term. So for each group and each feature, you have, and so this is, for example, maybe test prep biases scores upwards for like group A students because they're more privileged. And so you have a bias term for the means, but then you also have a variance term for this distribution. And the variance term can, again, be dependent on the feature in the group. So certain features might be far less useful for one group than another. For example, for people from really rich high schools, you might just know, and okay, so I'm about to say something that might sound ridiculous, but so the high school across from Stanford University sends about 30 kids a year to Stanford, right? Stanford for undergraduate, not for graduate admissions. And so basically Stanford knows everything about that high school. They know the teachers, they know exactly how to read the faculty, the letters of recommendations. They can have a really precise estimate on the top students of that high school. And of course, there's some bias going on in there too, but the variance is also down compared to, students from other high schools. And okay, so from these features, then the school is going to just estimate the skill in the Bayesian optimal manner, and then it's going to admit the best, the sort of the students with up to a capacity C. And the things I wanted to point out is just so there's bias terms in the features. For example, test preps can shift things upwards. Here we just assume that the school knows these biases. So when the school is doing the Bayesian estimation, it can cancel out these biases perfectly. On the other hand, this variance is something that you cannot correct for. So this is this is like an information theoretic lower bound for just like, if there's variance in these estimates, even if I know the distribution of the variances, there's just nothing I can do. And without loss of generality, we just assume that the group A students have less variance overall. And so this is just the technical way to say that, but it's just saying that students from familiar schools are going to be easier to analyze. And then finally, we want to model these access barriers. And we say that a fraction of students don't have access to this final test score. And so this test score is hidden because they don't take the test, or they don't have the money to report their score because, it costs a lot of money to report test scores. And so if the school is going to require these test scores, then there's a bunch of students who cannot apply to the school. And so the school actually observes a censored set of applicants. Okay, cool. So, okay, yeah. Okay, and then I will have to. Okay, so in this paper we look at sort of two competing policies. We say you can drop the test, but you only now observe a subset of features, theta 1 through theta k. But then all students can apply. Or you can keep the test and you observe all the features, but only a fraction of students can apply. Now, of course, there's a missing policy here, which is you can make the test optional. And so for some students, you have all the features, and but for some students, you don't. The problem with analyzing that in the same paper is then you really have to think about student strategic behavior, right? You really have to think about how are students going to decide whether to report their test score or not. And I actually end up doing that with a different student in a different paper that we're about to post online. But for this paper, let's just assume that sort of these are the two policies that you can think about. And then we ask, how does this decision of choosing one of these two things affect what we call academic merit, which is just the sort of the expected skill estimate of the students that you end up admitting? Or how does it affect what we call the diversity level, which is the fraction of group B students in the admitted class? So there's the fraction of group B. So the group B students are the ones that we're saying are sort of the more disadvantaged. And we're saying, does the fraction of them match the true fraction in the population? And then we also care about individuals. So if you condition on the skill level Q, is there a difference in admissions probability between two students of the same skill level, but who belong to different groups? And this is basically saying that you might have heterogeneous differential effects for students at different parts of the distribution. And then, of course, all these research questions are going to depend on the model parameters. And we are particularly thinking about care about what is the effect of the variances and the access levels. Okay, so what I really like about this paper is that, yes, there's like a lot of math and the appendix is long and the calculations are annoying, but it's really easy to explain sort of the theoretical ideas by just looking at pictures. And so that's what I'm going to do now, maybe for the next 5 or 10 minutes, instead of showing through algebra that no one wants to see, I'll just try to explain what's going on here. Okay, so what I'm going to show you is a lot of plots that look like this, where one axis is going to be the skill estimate. So what is the what is the estimate of what is the skill estimate of the student that the school had? And the y-axis, the vertical axis, is what is their true skill level. So they had some true skill level, they came up with features, and then the school came up with a feature estimate and a skill estimate, and then I just look at the joint distribution. And this diagonal dotted line just means perfect estimation, right? So if there was no variance, then the school could just perfectly back out the function from the data that it receives. Okay, but we're not going to be on the perfect diagonal line. And then the school doesn't observe the y-axis, it only observes the skill estimates. And so the best thing it can do is have a threshold where it admits all students above some threshold. And so everyone in this gray box is who's admitted. Okay, so this is something what that joint distribution looks like, right? Is that you're going to have some distribution that it turns out, and I'll explain why in a little bit, is actually not, sorry, is not centered on the diagonal line, but it's actually close to it. Okay, and so this is a very ugly formula. I mean, it's actually not that complicated, but this is just what the skill estimate looks like for a given individual student with these features. And what I want to point out here is that the skill estimates can cancel out the bias term perfectly, but the variance term is still sort of, the variance terms are what end up dominating. And it's hard to see what's going on with these individual skill estimates. And so what I showed you now above, and this is what's actually being plotted, is what is the, so actually not them, this is what's being plotted up here in the plot above the joint distribution, which is the marginal distribution of the skill estimates. And something that's interesting to note here is that the marginal distribution doesn't depend on the bias terms because those got canceled out, but it depends quite heavily on the variance terms. And so even though the school knows the population, so, and this is different than the marginal distribution of the true skills, right? The school knows that students are distributed according to this marginal distribution. But when it comes up with its skill estimates, its marginal distribution ends up being very different than the sort of what it thinks, or what it knows the students are truly distributed as. And in particular, it's weighted down by the precision, by the variance that I was saying earlier. And so the noisier that the skill estimates are, the noisier that data is, the smaller this is going to be. And so the sort of the more tightly concentrated around the mean that features are. And so let me display what's going on there. And so this is that plot. So I have two sets of students, where the pink has higher variance features, and the green has lower variance features, so really precise features. And so what you can see is that the pink's marginal distribution is centered closely around the mean of 0. And if you think about the joint distribution, it's being rotated away from the diagonal. So you're just rotating the joint distribution away from perfect estimation. And the reason that's happening is because one way to think about it is with more feature variance, you're regularizing each individual's person toward the mean score. So in the extreme case, suppose that you had absolutely no data on anyone, right? You just had, like you just saw a list of names and you had no data. Then the best you could do for each person, individual person, is say, you know, this person's score is at the mean. And you're going to be correct on that individual level, but you're going to be wrong on the population level. Okay. And so that's exactly what's going on. And then and because of that, you end up seeing fewer students in group B at the tail of the marginal distribution. And so you would end up admitting fewer students. And then what the individual fairness gap is saying is, now let me condition on this. Let me condition on a true scale of 2. Then how many of those students are admitted? And again, we see a gap here, and that more sort of blue students or green students are admitted than our pink students. And so this is why there's an individual fairness gap, and that there's a rotation going on. And what's interesting is that if you just consider students above 0.5, this gap is biggest at the extremes, right? So the rotation makes the gap as big as possible, sort of fairly big in the extremes. And that's what we end up finding theoretically. Or not exactly at the extremes, but close to the extremes. The gap ends up going down again at the extremes. And this is exactly what that the newspaper quote that I said at the beginning was trying to get at. Is it's really hard to identify these students at the extremes if you have less information about sort of a subset of them. Okay. On the other hand, so that is everything about variance. On the other hand, what happens if you have differential access? So one group of students has sort of less probability of having a test score. And so in our distribution, in our model, what that ends up happening is you just see fewer students from that group. And so the joint distribution looks the same in terms of the shape, but it looks smaller. It just like there's just less mass there. And so that's what's going on. And so really the choice of the school is choosing between these two worlds. It's choosing between a world where you're fine with this rotation of the distribution, or a world where you don't want it rotated, but then you just have a smaller mass. And sort of everything technically is going to sort of all the theoretical results is trying to compare the two, is comparing sort of these two alternatives in sort of, yeah, theoretically. And then, you know, I'm happy to stay on for some questions afterward. Okay. So yeah, so because of that, I think I won't talk about the data part. I'll just talk about the theory, or you know, we'll see what happens. Okay. So informally, so the first the first theorem is probably going to be completely unsurprising, which is that we simply have more information for group A. That because we have more information for group A, you know, group B students are going to be underrepresented. That this process is going to have fewer students at the tail, and so less are admitted. What's interesting is and then the other thing is especially amongst high skill students is where the gap is the highest skill students from group B are the ones who have lower admissions probability from the same skilled students in group A, and that sort of explains the diversity level, but that also is potentially problematic in its own right. And what that also explains is we also just have worse targeting amongst disadvantaged students. And so in particular, you know, you're admitting some level of disadvantaged students. And what we're saying here, what this theorem is saying is amongst the ones that you admit, you're actually not admitting the ones with the highest true skill estimate Q, just because of the noisier estimation. And this is exactly because of the rotation effect. And so this theorem is not comparing it to the other distribution yet. All I'm doing is just sort of characterizing what happens because of the rotation. Great. Okay. So the math is going to be missing now, but I don't think they're particularly insightful anyway anymore. Okay. So there's also just a missing slide. Oh, interesting. Okay. So yeah. So okay. I'll let me just go to go to this slide. So what this is saying is now, okay, so in the previous slide we said, okay, so what happens if you drop the test score when you didn't have barriers? And so I only had to think about the rotation effect. Now I'm saying what happens if I drop the test score? But I also have to think about the fact that before I dropped the test score, there were some students who weren't applying. And so if I drop the test score, then there's going to be more students who end up applying. And I saw that there was a question in the chat that are the group B students the one who are not evaluated by the test? Kind of. So the group B students are the ones who fewer of them are not evaluated by the test. And so like some of them are, but some of them aren't. And so we just had to do that because sort of if none of them are, then like all the effects are super strong. So you have to say that maybe like empirically in the data, that I shared at the beginning in the US, one paper would suggest that 70% of students, of like lower income students, had access to the test, but 30% did not. Okay. And so what we find is when you drop the test, really you have to look at, there's now a data dependence on what the effects are, if there are barriers. And so you can say, here's the parameters of the model, and it's two-dimensional. And in one region of the model in particular, when sort of most students had text access, and or the data was very so. In one context, the dropping the test is going to be harmful. In another context, dropping the test is going to be very helpful. And it very much depends on what is the relationship between the variance of the test score, so how much information was it providing, and the group B test access. So how many students did not have access to the test. Okay, I'm going to skip this, and then briefly just go to the data. I'm going to do 2 minutes, and then I'm going to open up to questions. So what data do we need if I want to see how all of this works in real life? You need some sort of data on student applications, right? So I need to sort of pretend I know the features of the student. So test scores, recommendation letters, high school performance, and so on. And then worse is I need some proxy for student skill. What we're going to do in this paper is admittedly a bad proxy, but suppose you observe that all of these students got admitted and you observed how they ended up doing. Then what was their GPA at the time of graduation, and how does that compare to the data that you received at the time of admissions? The challenge for those of you who know causal inference and do causal inference is, of course, that we need outcome data to do this. We need outcome data for students who, not just for those who are accepted and enrolled, but for every student. And this is a challenge to have in practice unless you're collaborating with an education ministry or something. And the reason this is a challenge is otherwise I'll just say this in causal inference terms, and then in plainer language, is you're conditioning on a collider. You're conditioning on the set of data that you receive, because only students that, for example, at higher test scores were the ones who ended up admitted and enrolled. Okay, and so we have some data. There's some public data available from what's called the Texas Higher Education Project that shows you a bunch of application data. So individuals' high school class rank, their standardized test scores, some amount of demographic features like how rich was their high school that they went to. And then we saw admissions and enrollment data. And then for the subset of students who enrolled, we also saw their GPA for every enrolled semester that they were in college. So this is quite rich data. And then I'm going to skip how we map this data to the model, but we constructed proxies for each of the things that we care about. And what I just want to show that we end up finding is exactly what we said in the theoretical results. Let's say we were in one setting where we did not have good information besides the test score. The test score was really providing us the best information. Then we see that in that case, dropping the test, even in this data set, is harmful for every objective. You end up admitting students who would have gotten a lower GPA, and you end up admitting a less diverse class. So you sort of disadvantage already disadvantaged students even further. But in a different setting, if you end up using a very informative feature that you have on some of these students, like sort of a different feature in the data set, dropping the test score is actually the right thing to do. If you drop the test score, you both admit students with sort of a higher average GPA, and you admit a more diverse class of students. And so you end up being helpful on every objective. Okay. And so, sort of just to summarize the paper, what we did was we modeled the trade-off between the beneficial information aspect of having more features and the exclusionary nature of some students not being able to apply. So you have less data and or like not less data, you have less sort of points to classify in your classification problem. And what we find is that dropping the test can either be detrimental or helpful to every possible feature. So there isn't a trade-off between diversity and academic merit. The sort of both of these objectives can move in the same direction. And then we think that the multidimensional machine learning framework sort of is also sort of quite useful in other settings beyond like thinking about standardized admissions. I'll just put the slide up here. I'm happy to take questions